Hey everyone, and welcome back to the channel. Have you ever wondered how websites like Amazon, Netflix, or even your favorite social media app can remember who you are, what you like, and show you personalized content in the blink of an eye? The magic behind all of this is something called a database. And today, we're going to dive deep into the fundamentals of what makes a database tick, drawing inspiration from one of the most respected books in the field, Fundamentals of Database Systems by Elmasri Navathe. So what exactly is a database? At its core, a database is simply an organized collection of related data. Think of it like a super smart, massive digital filing cabinet. But instead of just storing files, it allows us to store, manage, retrieve, and update information with incredible speed and efficiency. The software we use to interact with this filing cabinet is called a Database Management System, or DBMS for short. This is the program that lets us talk to the database, ask it questions, and tell it what to do. Before databases became what they are today, people used what we call the file-based approach. Imagine every department in a company having its own set of files. Sales has their customer files, accounting has their payment files, and so on. This might sound okay, but it led to huge problems. The first issue was data redundancy. The same customer's name and address might be stored in multiple different files. If that customer moved, you'd have to update it in every single place, which is a nightmare. This leads to the second problem, data inconsistency. If you forget to update one of the files, you now have conflicting information. Which address is the correct one? This lack of a single source of truth was a major headache. On top of that, it was difficult to access data. If you needed a report combining sales and payment info, you'd have to manually go through separate files and piece it together. Security was also a big concern. It was hard to control who could see or change what information. This is where the database approach comes in and saves the day. Instead of scattered files, we have one central integrated repository of data. A DBMS sits on top of this repository and acts as the gatekeeper. This solves all the problems we just mentioned. With a DBMS, we can control redundancy by storing a piece of information, like a customer's address, only once. This automatically ensures data consistency. The DBMS also provides powerful tools, like query languages, to easily access and combine data from different parts of the database. Security is massively improved because the DBMS allows for fine-grained access control. You can specify exactly who can view, add, modify, or delete specific pieces of data. Plus, a good DBMS ensures data integrity, meaning it enforces rules to make sure the data being entered is valid, for example, preventing you from entering a letter in a phone number field. It also handles backups and recovery, so if the system crashes, your data isn't lost. Now let's talk about the different kinds of people who interact with databases. You have the Database Administrator, or DBA. This is the person in charge of the whole show. They design the database, manage security, monitor performance, and handle backups. Then you have the database designers, who are the architects. They communicate with the users to understand their needs and design the logical structure of the database. Next are the end users. These are the people who actually use the database on a daily basis to get their jobs done. They can range from a bank teller using an application to a data analyst writing complex queries to find business insights. Finally, you have the application programmers who build the software that end users interact with. They write the code that sends requests to the DBMS to fetch or store data. To really understand how a database is structured, we need to talk about the concept of a data model. A data model is like a blueprint. It describes the structure of the database, the relationships between different pieces of data, and the constraints or rules the data must follow. There are different levels of data models. At the highest level, we have conceptual models, like the entity relationship or A model. This is a high-level view that's easy for people to understand. It focuses on identifying the main things we want to store data about, which we call entities like student or course, and how they relate to each other like a student enrolls in a course. Below that, we have the logical models. This is where we get more specific about how the data will be organized. The most popular logical model by far is the relational model, which was a revolutionary idea proposed by Edgar Codd. In the relational model, data is organized into tables, which are also called relations. Each table has rows and columns. A row, also called a tuple, represents a single record like one specific student. A column, also called an attribute, represents a property of that record like the student's name or ID. Every table has a primary key, which is a unique identifier for each row. For example, a student ID would be a perfect primary key because no two students have the same ID. This ensures we can always pinpoint a specific record. Relationships between tables are established using foreign keys. A foreign key is a column in one table that refers to the primary key of another table. For example, in a course enrollment table, we would have a student ID column that is a foreign key referencing the student's table. This is how we link a specific student to the courses they are enrolled in, creating a powerful interconnected web of data. The language we use to communicate with relational databases is called SQL, which stands for Structured Query Language. SQL is the standard for managing relational data. With SQL, you can do everything. You can define the structure of your tables using data definition language, or DDL with commands like create table. You can manipulate the data itself using data manipulation language, or DML with commands like select to retrieve data, insert to add new data, update to change existing data, and delete to remove data. For example, if you wanted to find all students majoring in computer science, you could write a simple SQL query like select name from students where major equals computer science. It's an incredibly powerful and expressive language. Of course, the relational model isn't the only one out there. Over the years, other models have emerged to handle different types of data. We have object-oriented databases, which are great for complex data structures used in programming languages. And more recently, we've seen the rise of NoSQL databases. NoSQL, which can stand for Not Only SQL, refers to a variety of database types that don't use the traditional relational table structure. These include document databases like MongoDB, key value stores like Redis, column family stores like Cassandra, and graph databases like Neo4j. These are often used for big data applications and situations where you need a lot of flexibility and scalability. So, to recap, we started with the messy world of file-based systems and saw how the database approach, with a centralized DBMS, brought order, consistency, and security. We learned about the key players, from DBAs to end users. We explored data models, focusing on the powerful and widely used relational model with its tables, primary keys, and foreign keys. And we touched on SQL, the universal language for talking to these databases. Understanding these fundamentals is the first and most important step for anyone looking to get into software development, data analysis, or data science. Nearly every application you build and every piece of data you analyze will involve a database. By grasping these core concepts, inspired by the foundational work of Elmasri and Navathe, you're building a solid base for a successful career in tech. I hope this overview has been helpful and demystified the world of databases for you. There's so much more to explore, but this should give you a fantastic starting point. If you found this video useful, please hit that like button, subscribe for more content, and let me know in the comments what database topics you'd like to see covered next. Thanks for watching, and I'll see you in the next one.